Floor is yours.
Thank you very much. Yeah, I would first like to introduce you to the people I did this work with. Here we have Arnoud van der Leer and Kobe Wullaert, who are master and PhD students respectively at TU Delft. And they couldn't be here, unfortunately, but so I'm here to represent them, but they did actually most of the work. So in this talk, I will mostly talk about Scott's representation theorem. I will not so much focus on the Karoubi envelope, just to focus on one particular topic. So to give a brief overview of what we have done in this work, this is just motivation. I think hopefully maybe you have heard of this correspondence between, on the one hand, simply typed lambda calculi, and on the other hand, Cartesian closed categories. And what is the connection? Well, we can consider a category of simply typed lambda calculi and a category of Cartesian closed categories. And there are functors back and forth, an interpretation functor and then sort of an internal logic functor. And it is one of the great insights of theoretical computer science, maybe that interpretation and internal logic form an equivalence of categories. And that's a very famous result. And I want to talk about a tiny sibling to this result, which is about the untyped lambda calculus, here represented by this lambda theory on the left-hand side. And on the other side, we have something that I call RO, the reflexive objects. So what is RO? RO is the collection of Cartesian closed categories equipped with a reflexive object. So what is a reflexive object? It's an object A that comes equipped with two morphisms, a morphism lambda from A to the A to A. You think of this as lambda abstraction. And the morphism rho from A to the A. Think of this as application, such that the composition rho after lambda is the identity. So this is the famous beta equality of the lambda calculus. So the result about untyped lambda calculus is not quite as strong as the one for simply typed lambda calculus, but Dana Scott in the 60s, I think, proved that any lambda theory comes, say, from some reflexive object. That is, for any lambda theory, we can construct a reflexive object in some category such that if I take the endomorphism theory of that reflexive object, I come back to the same or an isomorphic lambda theory. Yeah, so this is not an equivalence here, but at least it's a section retraction pair between untyped lambda theories and reflexive objects. The result was proved first by Dana Scott, was written up in a paper in 1980, and then Martin Hylen in 2012, he wrote a paper called Classical Lambda Calculus in Modern Dress, where he revisits this result and proves it kind of differently. And it is about the difference of these two results by Scott and Hyland, or these different constructions, that I want to talk about and how to compare them. How can we actually relate these two constructions that they did? So to summarize our work, I would like to talk about the formalization of the constructions of Scott and Hyland in univalent foundations, in Unimath in particular, which is a ROC library of univalent mathematics. Then I would like to explain how one can compare these constructions of Scott and Hyland to each other. And this will make use specifically of features of univalent foundations. And finally, if I have the time, I will talk about a tactic that Arnoud van der Leer implemented to automatically rewrite lambda terms, which was used in the formalization of Scott's construction. Okay. So this talk takes place in univalent foundations, so I will give a brief introduction to univalent foundations. Nothing that I will discuss in this section is original. So what is univalent foundations? It's a Martin-Löf type theory plus the univalence axiom. An important concept that is not an extension of the theory, but something that can be defined within the theory of the basic Martin-Löf type theory is the concept of homotopy levels. So we call a type X a set if it satisfies the uniqueness of identity proofs. And of course, we do not assume axiom K in Martin-Löf type theory. So that is a proper, not all types are sets, of course. We call a type a groupoid if all the identity types are sets. Yeah. So if for any A and B, the identity type A equals B is a set. And then the univalence axiom that you might have seen before. I'm giving here sort of I'm being sloppy here. The proper formulation of the univalence axiom is that we have a canonical map from X equals Y for types X and Y, defined by identity elimination. We map the reflexivity to the identity equivalence on X equals Y. And the univalence axiom says that this map is an equivalence. So it says that identity of types is the same as equivalence of types. Yeah. Okay. Now, when we develop category theory in univalent foundations, the fact that not all types are sets is interesting and leads to a choice that we'll have to make. So we start with what is a category. A category C consists of a type of objects, C naught, and a family of sets C, A, B for any two objects A and B. So here, asking that the morphisms C, A, B form sets is clear why we need this. The axioms of a category talk about equality of morphisms, so we want these equalities to be unique if they exist. But the type of objects a priori is not requested to be a set. We also want composition and identity, of course. And then we have on a category, we have one piece of data that is not kind of relevant somehow, which is the identity types on the type of objects, C naught. The identity type on this type is sort of information that we want to get rid of. And there are two ways to get rid of this information. We can either ask that C naught is a set, and then we call the resulting category a set category. Or we can ask that the identity type coincides with the type of isomorphisms in the category. And then we call the resulting category a univalent category. Yeah, so there are two ways of getting rid, in some sense, of the identity type on objects. In a univalent category, the type of objects is then a groupoid, one can prove. So this difference between set category theory and univalent category is important for the purpose of my talk. We have set category theory where constructions on categories are invariant under isomorphism of categories. And examples of such set categories are finite categories or categories built from syntax. And we have univalent category, on the other hand, where constructions are invariant under equivalence of categories. And many examples of categories that arise typically are univalent. So we have a category of sets, a univalent category of sets, of groups, of rings. We have a univalent category of set categories, for instance, and so on. Okay. Importantly, we have something called the rest completion that allows one to transform, not transform, but to construct a univalent category from a category, not necessarily univalent, not necessarily a set category. So we have sort of a free univalent construction of a univalent category that satisfies the universal property of a quotient. So if C is any category and D is a univalent category, then any functor from C to D factors uniquely via the rest completion of C, which is a univalent category. So that provides a systematic way of turning a set category into a univalent one. Okay. So that was just a brief review of univalent foundations. Now I come to the topic of lambda theories and Scott's representation theorem. So this is the picture that I would like to explain. We have lambda theories that I have not defined yet. On the one hand, we have the collection of categories with a reflexive object on the other side of this picture. And then we have a function called endomorphism theory that produces a theory from a reflexive object. And we have two functions in the other direction, one constructed by Hyland and one by Scott. The constructions that we formalized this picture in particular, the constructions we formalized are all taken from Hyland's classical lambda calculus in modern dress. The translation into univalent foundations of these constructions was mostly straightforward. And then where there's maybe a piece of new mathematics and where I would also like to advertise univalent foundations to you is in relating Scott's and Hyland's construction. So this is the bit complicated definition of what a lambda theory is. We first start with the definition of an algebraic theory. So an algebraic theory is consists of a sequence of sets Ln. Think of Ln as the terms with n free variables. Yeah. We have variables. So every variable gives rise to a term. We have a substitution operation of suitable type, and then we have laws for the substitution. Essentially, an algebraic theory is, I think, the same as a relative monad from finite sets to sets, something like that. And then what is a lambda theory? A lambda theory is an algebraic theory that in addition has abstraction. So family of functions lambda n from Ln plus 1 to Ln. So this is a construction binding a variable. Application is a construction, say, freeing a variable going from Ln to Ln plus 1, satisfying some laws that are not particularly important now, and importantly, beta equality. So we want that if we first do lambda abstraction and an application, that is the identity on Ln. Given a lambda, given a reflexive object in a Cartesian closed category, we can construct an endomorphism theory from this reflexive object. The terms of the theory are sort of given by morphisms into the object from x to the n to x. The variables are simply the projections. Substitution is just playing around with products, really. And abstraction and application can be constructed from, well, the lambda and the raw that we have as part of our reflexive object. The details are not so important. So we know now approximately what the lambda theories are, what this is, the reflexive objects, and the endomorphism theory, the theory generated by reflexive object. And now Scott produced a function from lambda theories to reflexive objects that is a section to the endomorphism theory function. And the construction goes approximately like this. He starts building a category from the terms in empty context. So the objects in this category are terms A, such that A composed with A is the same as A, so idempotent terms. And the morphisms from A to B in this category are, again, terms in L0, so terms with no free variables, such that B composed with F composed with A is equal to F. The resulting category is Cartesian closed. And then to find a reflexive object in this category, Scott chooses the identity lambda x dot x, this lambda term. And then he shows that starting with a lambda theory L, if we apply this construction and take the endomorphism theory of this resulting reflexive object, we get something that is equivalent or isomorphic to the lambda theory that we started out with. Hyland's construction is very different in nature. Given a lambda theory L, Hyland considers the category of presheaves over the Leer theory induced by L. The details are not so important here. This category happens to be Cartesian closed because it's a presheaf category. And then as a reflexive object in this category, he considers something that's the presheaf theory, the theory presheaf induced by L, which happens to be a reflexive object. And again, this construction is a section to the endomorphism theory. So what is important here, the details are not important, but what I want to point out is that this here is a very syntactic construction given by Scott, playing around with lambda terms essentially. And this is a very semantic construction. Our goal was to relate these somehow. Yeah. Hyland in his paper does not say much about, or anything really, about how his construction relates to the construction by Scott. So in this table, I have summarized again the two constructions. And our result is, I summarized here in this theorem, say, that is supposed to relate now Scott's construction and Hyland's construction. So how do I read this diagram? If R is the category that is produced by Scott, well, first of all, it's the category produced by Scott can be shown to be a set category, which also confirms this intuition that it's something very syntactic. Whereas the category considered by Hyland is this PL here. This category is a univalent category, which confirms the intuition that is something semantic or category theoretic. And then these two categories are related by the rest completion. We can show that R is actually is equivalent to a category that is the Karoubi envelope, whatever that is, of a category built from the empty terms in empty context. And there's a set theoretic Karoubi envelope, and there's a univalent Karoubi envelope, where the univalent Karoubi envelope is the rest completion of the set theoretic Karoubi envelope, or the set categorical Karoubi envelope. So what we have constructed is an embedding, say, of Scott's category via the rest completion into Hyland's category. And if you follow the reflexive object that Scott produced in R, if you follow that object along these functors here, you end up with the reflexive object that Hyland produced. Okay, so again, the intuition, or this informal intuition that Scott's construction is very constructive and Hyland's construction is very categorical, it can be made somewhat formal in univalent foundations with the observation that the category that Scott is manipulating, constructing, is a set category, whereas the category that Hyland is constructing is a univalent category. Okay. I will briefly talk about a tactic that Arnoud implemented when formalizing Scott's construction. Scott's construction, as you have seen a little bit, is requires manipulating lambda terms a lot. The manual rewriting that is required is tedious, but on the other hand, in Unimath, we don't like automation so much. So that was led to some conflict, and Arnoud was not happy with the state of the situation. So he programmed a tactic that produces a proof script with a sequence of refined tactics, essentially with a sequence of rewrite tactics. In this way, I think I have some screenshots here to explain how it works. Suppose we want here to prove something about lambda terms. So L is a lambda theory, and T is a family of lambda terms. Then one could try to prove something about a substitution. Sorry? I'm sorry, I think this is a screenshot, so it's not very interactive. Yeah, I did not want to mess around with the proof. Yeah. So here, it's maybe the details are not so important. On the right hand, what we want to show is an equality between lambda terms, essentially. Okay, so this goal here on the right hand side is an equality of lambda terms. So there's an equal sign here, and on the left hand side there's something lambda e, and on the right hand side there's something lambda e. And all of these equalities take place within a lambda theory L. Yeah. So we could either do a lot of manual rewriting to solve this goal, or we apply this tactic propagate subst, which does not actually, well, it changes the goal, but also it prints the sequence of tactics that it has produced. And the sequence of tactics is essentially a sequence of very fine-grained rewrites. Yeah. And what we then do in order to avoid having the automation built into the proof script is we replace the call to this automated tactic with the tactics, with the sequence of tactics that it has generated. So we comment out if we want this call to propagate subst. And in the end, when we run this sequence of tactics, the goal is essentially solved. We just have to apply reflexivity once. So this, what are the benefits of doing this kind of rewriting in such a weird way? Well, it's fast because the proof search takes a long time, but executing all these rewrites manually does not. So if we do the proof search once and then replace the proof search with the sequence of tactics that actually do the rewriting in a very surgical way, we save some time. It's modular in the sense that it's built from tactics. It's built by composing a bunch of smaller or generic tactics. It is extensible in the sense that we can add more constructions on the fly to the tactic and more equations between different constructions. So it's not restricted to lambda theories if we want. And it's generalizable in the sense that we were able to use or to adapt the tactic to do rewrites in a different domain of application. Things to improve in this tactic, of course, you've seen it's awkward to use. There would be we would benefit from some user interface improvements, and it's not complete. I've kind of chosen very well the problem that I showed you. There are other goals that are not solved entirely just by using this tactic. So there's still some stuff to be done. Okay. With this, I come to the end of my talk. I want to summarize a little bit the formalization. The code that we have written, it's integrated into the Unimath library. It consists of a little bit more, I think, than 11,000 lines of code, a lot of which goes, as you can see here, into the reasoning about lambda terms. This is because the surgical rewriting uses a lot of tactics. And since we do build a bunch of complicated categories, we use the technology of displayed categories to build up these categories in small layers. Okay, and so as a summary, this is what we have formalized, this picture. And then we have tried to, or it's a viewpoint that I would like to advertise, that the intuition of the difference between Scott and Hyland, the syntactic versus categorical method, it can be formalized somewhat in univalent foundations as the difference between set categorical, like working with set categories versus working with univalent categories. And finally, I've showed a tactic for rewriting that works for us, at least. Thanks a lot.